In this experiment, we are going to find the specific latent heat of ice. Specific latent heat of ice is the amount of heat required to convert ice at 0 centigrade into water at 0 centigrade. So the method we are going to use for that is called method of mixtures. So all the experiments in method of mixtures, there must be a calorimeter. As you can see, this is the calorimeter. So the calorimeter should be well heat insulated. As you can see, there are two containers. These are metal containers. The one outside this and other one is inside this. And the calorimeter inside is placed on two heat insulating pegs. The space between the calorimeters is filled with a heat insulating material. As usual, there's this stirrer and the thermometer. And about 2/3 of the calorimeter should be filled with water. So what we are going to do is, we are going to add a sufficient amount of ice and let it liquefy inside it. Since the ice is at 0 centigrade and the calorimeter and water is at room temperature, about 25 centigrades, the ice is going to absorb heat from water and the calorimeter. So we can write an equation like heat absorbed by ice is equal to heat supplied by water and the calorimeter plus stirrer. So that is the equation we are going to use. And using that equation, we can find the latent heat capacity of ice. Okay, now let's consider how to do this experiment in details. Okay, first let's consider the materials and apparatus required for the experiment. We need the calorimeter, then thermometer, a stirrer, water, and a sufficient amount of ice chips, filter papers, a chemical balance, 4-beam balance, and a box of weights. So we can arrange this setup. Then let's consider how we are going to use those materials and apparatus in the experiment. So the first step is to measure the mass of empty calorimeter. Let's say that measurement is M1. Then we are going to fill this calorimeter about 2/3 of its volume and measure the mass of calorimeter with water. Let's say that measurement is M2. So if we subtract this value from this value, we can get the mass of water only. So that is M2 minus M1. M2 is the mass of calorimeter with water. This is the mass of calorimeter, mass of empty calorimeter. So if we subtract those two values, we can get the mass of water only. Also, you have to measure the temperature of the water. It is closely about room temperature. Let's say that measurement is θ1. So this is the initial temperature of water. Then we have to add ice pieces. Before adding ice pieces, you have to make sure that the ice pieces does not contain any water. So we have to wipe the ice chips with the filter papers before adding this into the calorimeter. When you add ice chips, those ice chips tend to float on the water surface. So those ice chips can absorb heat from air as well. You have to prevent it. So to prevent that, you have to hold these ice chips down using this stirrer. This stirrer is a special one because this part contains a net. So we call this stirrer net square stirrer. So using the net square stirrer, we can hold these ice chips down and do the stirring. When you are adding ice chips, you have to do it one by one. First add the ice chip and stir the whole thing till it completely dissolves before adding the another ice chip. So you can maintain the temperature drop. Once the temperature has dropped by about 5 centigrades, you have to stop adding ice and record the minimum temperature. Let's say that temperature is theta 2. So this is the minimum temperature of the system. When you are taking the minimum temperature, there's another thing that you have to consider. You have to make sure that this minimum temperature does not go below the dew point. So initially you have to measure the dew point of the room. So if the temperature of the system goes below the dew point, there can be dew depositing on the calorimeter surfaces. So it can cause an error. So to prevent that, you have to make sure that this temperature remains above the dew point. So now you have stopped adding ice and took all the temperature measurements. Finally, you have to measure the mass of calorimeter with its all content. Let's say that measurement is M3. So M3 is the mass of calorimeter with all the components. Or after adding ice, this is the mass of calorimeter. So M3 is the mass of calorimeter after adding ice. So in this case, there is water, ice, and the calorimeter. This M2 is the mass of calorimeter plus water. So if you subtract these two values, that is M3 minus M2, this gives us the mass of ice. The mass of ice. So this is mass of water. M2 minus M1 is mass of water. M3 minus M2 is mass of ice. So these two values are going to be important when we are writing the equation for heat calculations. As you noticed earlier, we needed two types of balances, a chemical balance and a four-beam balance. So four-beam balance can be used to take these measurements, M1, M2. But this M3 measurement, we are measuring the water calorimeter plus ice. The mass of ice required for the experiment is very small. So we need a more accurate balance when we are taking this M3 measurement. So this M3 minus M2 is the mass of ice. So for that, when we are measuring M3, we need to use the chemical balance. Okay, now we have all the measurements required to find the specific latent heat of ice. Okay, as I mentioned earlier, in this experiment, ice is going to absorb heat from water and the calorimeter. So you can write an equation. So let's write an expression for heat absorbed by ice. So when ice absorbs heat in the experiment, first ice has to melt into 0 centigrade water. Then that 0 centigrade water would come to the temperature theta 2. This is the minimum temperature of the system. Since they are coming to the thermal equilibrium, that melted ice or water, 0 centigrade water, has to reach theta 2 temperature. So first, when we write heat absorbed by ice, we have to write the mass of ice, that is M3 minus M2 times capital L. Capital L is the latent heat of ice. So this is the heat required just to liquefy ice into water, 0 centigrade water. Then that 0 centigrade water amount should be M3 minus M2. So it has to reach this temperature. Then we are going to multiply this by specific heat capacity of water and the temperature difference. So this water was at 0 centigrade and now it is at theta 2 temperature. So the temperature difference is theta 2 minus 0. So these two terms shows the heat absorbed by ice. Then we are going to write an expression for heat supplied by water plus calorimeter. Okay. So the mass of water is M2 minus M1. M2 minus M1. This is the water inside the calorimeter multiplied by the specific heat capacity, then the temperature difference. Initially, the water was at theta 2, now it is at theta 2. So the temperature difference should be theta 2 minus theta 1. This is the heat supplied by water. And then we have the calorimeter. Calorimeter also supplies heat. Let's say the mass of calorimeter, that is M1. That is the mass of empty calorimeter. Then the specific heat capacity of calorimeter materials. Then also it should be multiplied by the temperature difference. That is theta 2, final temperature of the system, minus initial temperature. So all these values, we took some of them as measurements. These ones M3, M2, M1, these are just measurements. And this CW, that is specific heat capacity of water, we can get from a data book. Then this TCL, also that is specific heat capacity of calorimeter material. So the calorimeter material could be aluminium or copper. So we have just substitute that value here, the specific capacity of aluminium or copper. Then all those values are known. All these values are known, except the value capital L. That is the specific latent heat of fusion of ice. So that is the amount of heat required to convert 1 kilogram of ice at 0 centigrade into 1 kilogram of water at 0 centigrade. So in this way we can find the latent heat of ice or the specific latent heat of ice. So when we do experiments using method of mixtures, we have to make sure that the heat exchange happens only between the set objects or between set substances. So in that case, we have to minimize the heat loss or heat absorbed from the surroundings. There's a method called compensation method in order to minimize the error caused due to heat coming from the surrounding. So in this experiment, we have to make sure that the heat exchange only caused between ice, water and the calorimeter. We only included those in the equation. So you have to minimize the heat coming from the surroundings. So using the compensation method, we have to get water that is about 5 centigrades above the room temperature. Let's say the room temperature is 25 centigrades. 25 centigrades. So for the experiment, we need to get water at about 30 centigrades. About 30 centigrades. Then the water is at 30 centigrades. So you start adding ice, so the temperature drops. First from 30 centigrade to 25 centigrades, then from 25 centigrades to 20 centigrades. So within this temperature range, from 25 to 30 centigrades, heat goes out of the system. Since these temperature values are higher than the surrounding temperature. When the temperature drops below 25 centigrades, the heat is provided by the surrounding. So since these ranges are same, this is 5 centigrades, this is 5 centigrades, we can compensate that the heat supplied to the surrounding is equal to heat provided by the surrounding into the system. So we can conclude that these values are cancelled off with each other. So that is the compensation method. We are going to use this compensation method all the experiments involving method of mixtures. Okay, that is it for the experiment. To clarify this concept further, you will have to do structure essay questions more and more.